So, Professor, I want to ask you,
Mm-hmm.
for the exam tomorrow, how
Mm-hmm.
gonna be like all question for recitation,
No, there'll be
like
like
all calculation, or like I mean,
there'll be 10 multiple choice questions, and then 6 sort of calculation, short answer type questions, and then 1 exceedingly difficult bonus question.
so 10 multiple choice, 6 calculation, and there is writing.
Yeah, I mean calculation and writing. Yeah.
And
Oh,
you
sorry.
said, I'm sorry, just I confused. You said 10 calculation and 6, sorry, 6 calculation and 10.
Five sort of essay calculation type questions.
Oh, okay. Could
10
you let me know?
multiple choice.
Okay, could you let me know, like, what essay about? Like, what do you mean? Like, explain or definition, or
I don't. What's your question?
how is your essay question gonna be?
Well, just like the lab exam, there's going to be a question, and then you do the calculations and answer it.
Okay,
Yeah.
I'm scared.
So
Okay.
going off of that question that she had about the exam, so does that mean that we're downloading it and then submitting it to
Yeah,
Canvas?
exactly the same way that the lab exam was. Yeah. So you can either write directly on it. I made sure that there's plenty of room for those of you who want to just print it out and just write directly on it. Or if you don't have a printer, just answer the questions on just a separate piece of paper and then submit that. Yeah.
Thank you.
No worries. Man, so it sounds like everybody understands everything because they just want to ask questions about what the exam is going to be.
I
Yeah.
want to ask you, I study now chapter 3. I read that when the electron go away from nucleus, it will have more energy. When it's absorbed, when it goes away from nucleus,
Mm-hmm.
it will have higher energy. When it's close to nucleus, it will have low energy.
Yes. So that just says that basically that the shells further, the electron shells further away from the nucleus are higher energy than the ones closer.
Okay, how about light? The electron release light when it's close or when it's away?
When it moves, so let me write this down. So wait a minute. So here's my nucleus, and then I have an electron. So here's one shell, here's another shell, here's another shell. So when I add energy to the nucleus, the electron will jump from here out to here. And we say that's the excited state.
Mm-hmm.
So it's absorbed energy at this point. So it's moved from a low energy shell to a higher energy shell.
Mm-hmm.
Then when that energy is removed and the nucleus or the atom relaxes and returns to what we call the ground state, that electron then moves back to where it was originally.
Okay.
And this energy difference, so this energy difference between this state and this state is reflected in the light that it gives off. And we can measure the energy of that light, and that tells us what the energy differences are between the higher and the lower energy states. So the light actually comes out of the atom when it lowers its energy, when the electron returns to the ground state.
Okay.
That's how Bohr measured all of the energy differences between the different shells.
Okay. I was looking at recitation number 5.
Okay.
And for the noble gas electron configuration, it's in number 14. For the sulfur ion. Oh no, the mercury ions. Sorry. Does it matter which noble gas?
Are you sure it was a mercury ion? Was it Mg plus? Or is it just MHG?
Oh, it's just Hg.
Right, so it's just the atom. Okay.
Yeah.
So the what's the atomic number of mercury?
80.
80, right. So it tells us we've got 80 electrons to deal with. So we want to do the noble gas sort of a summary without all the electrons in it. We sort of want to just break it down by noble gas and then whatever's left over. We find the noble gas that is smaller than mercury. So we look and we see that mercury is in the 6th row. So it's in period 6. So what we want to do is find the noble gas in period 5, or row number 5. And you know what that one is?
Xenon.
Yep, xenon. So xenon, so we go square bracket, xenon, and xenon has 54 electrons. So basically we're going to start from there. So we start from there, and we just, so xenon, and then we go down to period 6, and then we just start 6s2, and then we just sort of basically follow the rest of the order until we get to, we keep going until we get out to mercury, and I think that ends at so that ends with it's a transition metal, so it's in the D block, and I think it ends with 5d10.
Yeah, that's right. I was just asking because at first I had a bit of confusion where I thought that I could use radon and then go from there.
No, but radon's bigger, so you'd have to go backwards. You have to take radon and remove electrons. It has to be the noble gas has to be smaller.
Okay.
And then we add electrons to it.
Got it. Thank you.
Yeah, and even if we had something like iodide ion. So iodine is 53 electrons, and iodide ion is 54, which is exactly the same number as xenon. So if we were going to give the noble gas configuration for iodide ion, we couldn't just say xenon. We have to go back to the one smaller than it, which would be krypton, which has 36 electrons, and start from there and go all the way. So we start with 36, and we'd fill in the description between 36 and 54. Because basically you have to shoot, whenever you do a noble gas configuration, you have to show all of the electrons from the previous noble gas up to whatever species you're looking at. Does that make sense? You have to go backwards, basically.
Yeah.
Yeah, if you're dealing with something in the 6th period, you have to go back to 5, or so the 4th period, you have to go back to 3, and so on.
Can we do question 13 from recitation 5?
Yeah, sure can. What is it?
Recitation 5, the following deal with write the noble gas shorthand electron configuration for Mercel.
We just did that one.
Oh,
Perfect.
sorry. I did not. It's okay. I will see the video. It's okay. Never mind. So we will.
So we can do a different one if you'd like.
Okay, we can do something from question 10.
Okay, I don't have it in front of me. I can look it up. So 10 from which recitation?
5.
Recitation 5. All right, just opening it now. It may take a second. Excuse me. All right. Number
10.
Number 10. Okay. I'll share that. So. All right, everyone can see the questions?
Yeah.
Okay, so I've had a few people ask me about these. It's a little confusing. The thing to remember, this is like the sort of take home on this sort of thing, is, where's my annotations? When you're thinking about the 4 quantum numbers, the first one, n, oh man, I need to make that darker. N refers to the shell.
Okay.
So that's where it is. 1, 2, 3, 4, 5, 6, 7. The second one refers to the subshell. Don't get hung up on what the official names for these are, because they're confusing names, like, magnetic and azimuth and principal, and yeah, that's just confusing. Think of it this way. So N is shell, L is subshell. We know what the subshells are. S, P, D, and F, right? There's only 4 of them. And so the addresses for those are 0, 1, 2, and 3. So there's only 4 numbers that L can be. And it just describes what this subshell is, okay? And then M to the L is the orbital. So we know that there's orbitals inside the subshell, and the number of orbitals depends on what subshell it is. And it's pretty straightforward to remember what the numbers for M to the L is, because what it is it goes from minus, let me change color here. It goes from minus L to plus L. So if you know what L is, M to the L, that's what the possible numbers are. So if it's S, that is 0. It's negative 0 to plus 0. Okay, it's just 0. If it's P, P is 1. So we know it goes from minus 1 to plus 1. And if it's D, which is 2, we know it goes from minus 2 to plus 2. That's the easiest way for me to, I can't remember I can't even remember the names of all the different numbers, but I do remember shell, subshell, orbital, and then the last one is just spin. So the last quantum number is the only one that talks about a specific electron. Everything else talks about groups of electrons. So the last one, spin, is the only description of a single electron. And it tells us whether it was the first one into the orbital, so it's plus 1/2, or whether it's the second one in, so it's minus 1/2. So just remember, shell. So that's just 1, 2, 3, 4, 5, 6, 7. subshell, 0, 1, 2, 3. Orbital inside the subshells. And you don't even need to memorize how many there are because you can just figure it out by using 0, 1, 2, 3 for the subshell name. It goes from -1 to +1, -2 to +2, -3 to +3, -0 to +0. That tells you how many orbitals there are in each subshell. And since there's only 2 electrons in each orbital, we need to define each one. First one in is plus, second one in is minus. Okay, so with that information, which question did you want to look at?
Let's do it all just to, I don't know if they are related to each other or no.
They're all related to each other. I don't understand the question.
That's why I don't want to skip one if we have chance to do it all.
Okay, yeah, we can, sure. So the number of orbitals, so that would be the third number, right? First one shell, second one subshell, third one's orbitals. So the number of different orbitals so n equals 3, so that we know that's 3. L equals 2, so what subshell is that referring to?
D.
P?
No, D.
D, right, D. And ML equals 0. So basically what it's referring to is one specific orbital. If m to the L is given a specific value, it means it's talking about one orbital. And in a d orbital, it's talking about this one. So if we were to draw it out, 1, 2, 3, 4. If we were drawing it out, it'd be this one in the middle. So the answer is just 1. And if you'd asked you the number of electrons that could have those 3 quantum numbers, the answer is 2, because there's 2 electrons in each orbital.
If it is N2?
No, if it asked you the number of electrons, if instead of orbitals, it said electrons with those 3 quantum numbers, the answer would be 2.
Okay.
First one would be plus 1/2, second one minus 1/2. So the second one just asks you for a subshell. So if it's a subshell, we know we're asking for S, P, D, or F. So n equals 4, that just tells us it's in shell number 4. So we just put, that says 4. So if L equals 2, again, what subshell is that?
D.
Yeah, so the answer would be 4D, not just any D, because it's a specific D subshell. It's the one at level 4. So it's the 4th shell, D subshell inside level 4. So it's 4D for that one. All right, number 3, the ML values for a D orbital. So ML, and that should say subshell. That is an error. Oh no, it isn't. Never mind. The ML values for a D orbital. So there are how many D orbitals? Or better question, what's the value of L? What's L for a D orbital? D subshell.
2.
2. So just by knowing that, we automatically know what the values of ML can be. So what are they? Because we know they go from minus L to plus L. So what are the possible values for m to the L? Because it asks for what are the ML values for a D orbital. So what can they be? If L is 2, m to the L is minus L to plus L. So what are my values?
-2, -1, 0, -1. Is that?
plus 1,
Yeah.
plus 2. Those are my 5 values it can be. So that's the answer for C. Okay? Now D, the allowed values for L for the shell n equals 2. So this tells us we're in the second shell. So n equals 2. And the maximum value, we haven't reviewed this yet, but the maximum value for L is n minus 1. That's the maximum value for L it can be. It can't be any bigger than that. So if n equals 2, if we're in the second level, it basically tells us how many subshells there can be. There can either be 0 or 1. It can't be 2. So it tells us there are 0 and 1. There's 2 subshells in the second shell, the second level.
For
So
that, I don't need to say -1, 0, and 1.
No, because it's asking you for the values of L.
Okay.
L is the subshell. Remember, it goes shell, subshell, orbital, electron.
Okay, if the question ML, if they ask me what's the value of ML for this question?
Which question? For D?
For D, yeah.
Oh, the allowed values. So the allowed values so there's 2 subshells, 0 and 1. So which subshells are those?
It's gonna be -1, 0, and 1?
Nope. No, yes, that's going to be the answer for that question. I'm asking you, what are the 2 subshells? If your values for L are 0 and 1, what are the 2 subshells that are allowed?
S and
In the next one.
D?
P.
P.
It goes S, P, D, F. So S and P. So S only has, as far as orbitals, only has 0, and P has -1, 0, plus 1. Yeah, so the allowed values for M to the L would be these 3. For the allowed values for L would just be 0 and 1.
Okay.
So E is basically the same question. So remember, the allowed values for L are maximum n minus 1. That's the largest value that L can be. And so if n equals 4, what are the allowed values for L?
Three?
Excuse me?
3?
Can't hear you.
3?
3 is the largest number. It can't be any larger than 3. So we can have 0, 1, and 2, and 3. Those are the. Remember, every shell adds an additional subshell. So 1 has 1, 2 has 2, 3 has 3, 4 has 4. And then so if it's 4, we're allowed all 4 values for L because there's 4 subshells in the 4th level.
So always L value is n minus 1, correct?
The maximum value is n minus 1.
Okay.
That's the maximum. And then everything less than that. So from 0 all the way to n minus 1.
Okay, when you ask me about ML, I should include negative, like -1, -3, negative, like this. Okay.
Yeah. Yeah, that's the only place other than the spin you'll see a negative number. So number of orbitals in a shell with n equals 3. So how many orbitals in n equals 3? So we figure n equals 3. So what subshells do we have? So L has a maximum value of 2, so we have 0, 1, and 2. In other words, we have S, P, and D. So how many orbitals in S?
0?
No,
Or 1, sorry.
1. How many orbitals in P?
1, 0, -1.
Right, so the total number? It's asking you for the number of orbitals. So you're right, the addresses for those orbitals are -1, 0, and +1. But how many are there?
3.
3. And then in D, how many orbitals are in D?
5.
5. So we just add them together. 1 + 3 + 5 is 9. That's why there's 18 electrons in the third level, because there's 9 orbitals.
So you said 1 plus 3 plus 5 is 9.
Mm-hmm.
Then because we have the negative of this, it's gonna be 18.
The negative of this? No.
Like, how you said 18?
It has 18 electrons.
Oh, okay.
Yeah, there's 9 orbitals and there's room for 2 electrons in each one. All right, so the number of orbitals with n equals 3 and L equals 1. So n is 3, L is 1. So we're dealing with 3. Which subshell is L equals 1? Remember, it goes 0, 1, 2, 3. So we're dealing with 3. So this is a subshell, so it's either going to be S, P, D, or F. So L equals 1. Which one is it?
P.
P, right, because that's 0, that's 1, that's 2, that's 3. So L equals 1, we're dealing with P. How many orbitals are in 3P?
3.
Yep, 3. Any P orbital, doesn't matter which one it is. Could be 3P, 4P, 5P, all the same. 2P. They're all 3 orbitals, -1, +1, and 0. All right. The maximum number of electrons that all have the quantum number n equals 3, so we're at level 3, and L equals 2. So L is the subshell, and it's 2, so which one is it? S, P, D, or F?
D.
D.
D. So 3D. How many electrons can we put in 3D?
6.
Nope, that's P.
Um,
Yeah, Sabrina, you had a question. Yeah, the answer's 10. Yes, since there's D is L equals 2, the possible orbitals are -2, -1, 0, +1, +2. So there's 5 orbitals, 2 electrons for each one. So the total number of electrons you can stuff into a 3D orbital or any D orbital is 10. Yeah. Sabrina, you had a question.
Oh no, I was gonna answer.
Oh, sorry. I'm sorry. Yeah, I was just going to have the hand raising for questions. If you have the answer, just belt it out. Be
Okay.
more than happy to hear the answer.
So the answer is 10.
Yes. So when n equals 2, L can be what? So again, oops. N equals 2. L, the maximum value for L is n minus 1. So what can L be when n is 2?
0 and 1.
Yep, 0 and 1. 2, level 2 is only S and P orbitals. So L can only be 0 or 1. Also, when n equals 2, the possible values for ML, and so remember, ML, we're talking orbitals. Shell, subshell, orbitals. We're talking for orbitals. What are all the possible values for m to the L when we're in level 2 and we have S and P subshells?
Negative 1, 0, 1.
Yeah, that's it. So S only has 0, and P only has -1, 0, +1. And those are the only two in level 2. So the three possible values are these. Okay? Yeah, good job.
And the number of electron is gonna be 6 for this, the one.
L equals 1, right, that's a p orbital, so that's going to be 6. And then n equals 3, L equals 1. So we're dealing with 3. So the name of that subshell would be 3 SPD or F.
P.
P. Yep. Yeah, just drill that into your, as long as you get the order of S, P, D, and F. I don't know if there's I should come up with some clever way to sort of, some sentence that has all those in it or something. But yeah, this is just the key. That's really the hardest thing to remember is S, P, D, and F. That's 0, 1, 2, and 3. So yeah, I'll have to come up with something, I think I came up with special puppies deserve food or something. I think that was the one I came up with last term. Because, you have 2 dogs, you think about it that way. So special puppies deserve food, S, P, D, and F.
What is the answer for K?
Number of electrons in 4, L equals 1. Which subshell is that? Which subshell is that? L equals 1.
P?
Right. 1. So 4p. I've got a 4p subshell. How many orbitals can I put in a p? How many orbitals, therefore, how many electrons? So how many orbitals in a 4p subshell? Or sometimes you'd just be able to, it'd be sink in your head when you're writing out these when you see electron configurations, you'll notice that it's always S2, D10, F14. What does it always say next to P? When you have a full P subshell, it's a number associated with it.
P6.
6, yeah. So when you're writing them out like over and over and over and over, actually that'll help sink it in pretty quickly. So 6 electrons. There's 3 orbitals, and each orbital holds 2. So the maximum number is 6.
Okay.
So the lowest value for N, where you can find a D subshell. So where's the first time we see a D subshell? So remember, each time we add a new shell, we go to a new level, we add another subshell. So we start with S. So where's the first time a D subshell shows up? So with 1, I have S. With 2, I have S and P. With 3, I have S, P, and something else.
D.
Yeah, 3D. So the first time I see a D is when N equals 3. That's the first time it shows up. And then 4 has a D, and 5 has a D, and 6 has a D, and so on. But the first time we see a D show up is in level 3. Okay?
Professor, I have a question.
C.
Number,
Okay.
when you say give two examples or list two elements that are examples of the following, do you
Mhm.
just want us to write the symbol and the name, or do you want us to do the electron configuration as well?
Well, I'll check and see that that's true, but as long as the question just says name two examples, that's really all you need to do. If it said name the examples and give the electron configuration, but it doesn't say that, right?
Okay, thank you.
Yeah. So, yeah, so basically, you know, if something like a half-filled subshell, what I'd be looking for is like something with the P3, because I know it's half-filled, because it should be 6, or a D5, because I know it's half-filled, it should be 10. So I would look for one of those in the periodic table.
Thank you.
Okay, no problem. Yeah, this is really good advice for, like, you know, especially if any of you go to court. Just answer what you've been asked. Don't answer anymore. That's you know, look at the question, see exactly what it's asking, because I can't take points off if you've answered the question, right? I mean, it's my fault if I didn't say give an example with the electron configuration. It didn't say that. Probably should have said that on a test. It probably will. Hint, hint. So yeah. So I can't take points off if you answer the question. I can if you get it wrong, but if you answer it correctly, that's it. Just answer the question. All right. Anything else from this particular? I guess you have the answers for 1 through 4. So
Can you post the answer for 5 and 6?
not yet, because people haven't submitted them,
Okay.
all of them yet. But you can answer. You know, we can ask anything about 5 if you like, or 6.
Okay. Can we do, let me see.
Right. If you guys aren't raising your hands, you're just going to ask all the questions. So look, get your hands up if you have a question. So, what you want to do, this one or recitation 6?
Can we do from question 11B?
And of recitation 5?
Yeah, question 11B.
11B?
Yeah.
Okay. All right, you want to know why? So you're saying B is
Yeah.
unacceptable?
Yeah.
Or which ones are unacceptable?
A.
That's right. What's wrong? A is wrong. What's wrong with A? Yeah, that is not correct. You can't have that. What's the problem with it?
So when n equal 3, L should be 2.
Yeah, L can't be negative.
Yeah.
L is either
L.
0, 1, 2, or 3. It can't be negative. Negative only comes into orbitals or spin. First two numbers can't be negative. All right, so what about B? You found a problem with that one. Or did you?
Number C.
Oh, that was quick. Who raised their hand there?
ML also should be not negative.
No, ML can be negative. That's the first two can't be negative. The second two can be negative. So ML minus 1, that's fine.
So in that question, we only need to encircle one, right? Like one answer, right?
Well, it says which sets.
Oh, okay.
So actually there is, I would circle B as well, because there's a problem there. I'm just asking you what it is. On a test, I would probably say, where is the unacceptable quantum number? So for the first one, the problematic one was this. That was wrong. Where's the error in the second one?
L can only be 0 or 1.
That's right. L can't be the same value as N. It has to be one less. That's the maximum. So L can only be 0 or 1 when N equals 2. So that is wrong. And there's nothing wrong with the third one. That just refers to 6 D 1, 2, 3, 4 minus 2. So it's that electron right there. Minus 2, minus 1, 0, plus 1, plus 2. So it's actually the very first electron into the 6D orbital. That's okay.
So the right answer, C, if you ask what is the correct one.
Yes, but I ask which ones are not correct. Now, on a test, I'd probably say explain. I wouldn't let you just say, it wouldn't let you just guess.
So if you want to explain C, why is correct? Because N, when N is equal 6, L equal 2, we said L is N minus 1, correct?
That's the maximum value it can be.
Oh, okay.
Yeah. It has to be smaller than N. So L equals 2, that's 6D. There's nothing wrong with that. So all right, someone had their hand up like a year ago. Like it just went up so quickly, I didn't see it. Like I couldn't read the name. Is there a question?
No, it's all good. You already answered it.
It's all good. Excellent. All right, any other questions? You want to do something from like the recitation 6?
Yes.
Might as well open it just in case. All right. All right, yay stoichiometry. All right, anyone have a question from this one?
Can we do number 3?
We can indeed do number 3. Let's look at number 3. Okay, yeah, perfect, good old-fashioned stoichiometry question. So what's the first thing you need to do when you have a stoichiometry question? Very first thing.
Write down what we have or what we know. Oh, no,
Yeah.
check if it's balanced.
No, that's fine. Yeah, we check as if it's balanced. I don't even see a reaction, so that's what I would say is, yeah, without a balanced equation, we can't do anything. So our reaction is magnesium plus nitrogen. And it's nitrogen, do you just put N?
Would it be N2?
Yes, it would be N2. And it makes magnesium nitride. So that's MgN. What's the formula for MgN?
MG3?
So
M2?
so the charge on magnesium is always something. What is it?
Plus?
2.
Yeah.
Remember, it's in group 2, so it's always going to be plus 2. And nitrogen, when it becomes an anion, it's always minus 3 because it's in group 5, and so it wants 3 more electrons to get to the happy place of 8 electrons. So it will be minus 3. So then we just do our applesauce crisscrossing, and so that would be Mg 3N2. Okay, so let's erase this. Right, so now we have a balanced equation, or do we?
No, it's not balanced.
It's not balanced. No, it isn't. So it looks like my nitrogen's balanced. I got 2 atoms on the left and 2 atoms on the right. So that's cool. But my magnesium isn't. So how many moles of magnesium do I need?
We put 3 in front of Mg in the reactants.
Yep. Yep. Yeah, and notice we don't put Mg2 plus. How come? Why don't we do that? I mean, that's the way we normally see magnesium, right? How come we're not doing that here?
Because it's not ionic.
Yeah, it's not, well, it becomes ionic. It's not ionic here because it says magnesium. So when we think of magnesium, we think magnesium solid. If it said magnesium ion, that would be Mg plus 2 aqueous. But it didn't say magnesium ion. So it's not that, it's this.
But the question from the beginning, why you put Mg3 in the product? Because it's
Because magnesium is plus 2 when it becomes ionized, and nitrogen is minus 3. So to balance these two, we need 2,
okay, got you.
3 magnesiums and 2 nitrogens. So we have a total of plus 6 and minus 6 to balance each other.
And then
All right, so now we write down everything we know. So we have 4.5 grams of nitrogen gas. So this would be, oops. This would be solid, and that would be gas. And then this would be solid. All right, so we have 4.5 grams of nitrogen gas. So what do we need to do with that information? We need to convert it to get to, we need to convert it to something. What do we need to convert it to?
we need to convert a gram of nitrogen to number of moles.
That's right, moles of nitrogen. Because reactions happen in moles, not in grams. So I want moles, and I want to get rid of grams. So I'm going to put grams on the bottom, and I'm going to put moles on top. What do I put for grams here? What number for grams am I using?
N2.
Yeah, but what about N2? What's grams of N2?
Molar mass.
Right, I want the molar mass of N2. So I go to my periodic table, or I can Google it. So 1, and I get, it's 14.0067. So is that the number I put in? Grams per mole.
14.0067, yeah.
Is that what I put in there?
No, you have to add one more since it's N2.
Right, it's N2, so I need twice as much. So that'd actually be 28.0 something. 32.013, something like that. Close enough.
28.0134.
Okay, so that is going to tell me how many moles of N2 I have. So how many is that?
.16071.
So 0 point, how many?
16071.
16071 moles. Okay, now we're getting somewhere. All right, so that's how many moles of nitrogen we have. Now this question basically tells us we have a limiting reactant problem. Which one's the limiting reactant?
Don't we need to calculate that on our own?
No, we don't.
Figure it out?
Just
Oh.
read the question.
Oh, magnesium?
No.
Oh, really? Oh, nitrogen.
Nitrogen. Yeah, just by, because it says we have 4.5 grams of nitrogen, and that's all we're going to have. So basically, the amount of product is limited by the amount of nitrogen we have. So we already know how many moles of product we're going to get. It's limited, it's limited by this number. It's limited by the number of moles of nitrogen. So what's the ratio of moles of nitrogen to moles of product?
1.
1. So how many moles of product am I going to get?
1.
Nope.
I mean,
3.
Nope. If there's a 1-to-1 ratio of moles of nitrogen to moles of product, how many moles of product will I make with that much nitrogen?
the same amount of the nitrogen moles?
Yes. That's how many moles of magnesium nitride I'm going to make. So now the question becomes, how many moles of magnesium will it take to make that many moles of magnesium nitride? How am I going to figure out that? So I need to multiply this number. So I have moles of magnesium nitride times something will give me moles of magnesium. What am I going to multiply moles of magnesium nitride by to give me moles of magnesium? And this is the number of moles of magnesium nitride right here. So we're going to multiply that by something to get me moles of magnesium. What do I multiply that number by? Remember, whenever you get stuck, remember kindly Professor James said that what I want, whatever you want is the final answer. You put that on the top, right, in the numerator. Whatever you want to get, whoa, that was loud. Whatever you want to get rid of, you put that in the denominator. So we want this in the numerator. We want to get rid of that in the denominator. So what am I going to multiply this by? I'm just going to sit here until someone tells me what to do. 'Cause it's
1
you.
over 3 or 3 over 1? I'm not sure.
You tell me. That's why I gave you the advice. Put what you want in the numerator. Put the information you want to get rid of in the denominator, so it cancels.
All right, we're just listening to everything now. Okay, it's 1:05. Let's get started. All right.
Whoa.
So
Who's this? Hello?
Let's see.
Hello?
Share my screen.
Okay. So, what am I going to multiply moles of product
All right.
to get moles of magnesium?
Oops, I forgot to
3
update
over
the.
1?
Oh, Wait,
title.
I think I, hello?
This is 9th. My bad. All right, we'll keep going. All right, so this one I think hopefully will be also interesting. This was actually Dorothy's idea to have people's pictures when they were young. We'll see. Some people, I feel like some people basically took a selfie. So
I think that's another
I don't think.
class.
I know. How do
So
we?
let's start with our kid pictures. This one.
Damn it! How do we?
Yan-Ming.
Yeah, I think so.
Yeah. Does it look like Yan-Ming?
Yeah, I don't
Yeah.
even think so. I can't recognize that.
Okay. So if you're in my class, please unmute yourself and answer the question.
You have to multiply the moles of magnesium nitrate by the molar mass. So it's going to be 3 mg.
No.
Oh.
Right. Oh, I see what you mean. We don't need the molar mass just yet. So we want, right. So on the top, we put 3 moles of
Yeah,
magnesium. And on the bottom, we put 1 mole of magnesium nitride. Because we go to the balanced equation. And so the ratio of product to reactant is 1 to 3, right? And so I have the amount of product. I want to get rid of moles of product. And I want to have moles of reactant. So I multiply this number by 3. So what is that? That gives me 0.16071 times 3.
0.48214229.
Dang, you like sig figs. Right. So yes, and by all means, carry them all. Carry all of them till you get to the end. They'll give you a more precise answer.
So when we do the exam, do you want us to just
Show
round
all
it,
your
or do you
work.
want it out?
No, I want you to carry all the figures through to the very end and then round at the very end. Okay? So I have 0.48213, blah, 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 something, I forgot. Moles of magnesium. And then you just convert moles of magnesium to grams. Because that's the question, right? It's how many grams of magnesium. So you just look up in the periodic table, right? You have moles of magnesium. What am I going to multiply that by? I want grams. I want to get rid of moles. Molar mass of magnesium, right? And that'll give me my answer. So how many significant figures would I report this in?
2.
2, right. I've only got 2. So whatever the number is, I would round it to 2 significant digits. Okay? Yeah, there's a lot in that question. Looks pretty straightforward, but yeah, there's a lot of work to do in it. It seems people have a real issue with these limiting reactant problems, sort of identifying which one is the limiting reactant. Here, we didn't even need to figure it out because we were told, basically, if we have this much of one reactant, how much of the other reactant will we need to precisely balance it? It's sort of like the lab you were doing when you had A, B, C, and D. If you know what the ratios are between A, B, C, and D, its products and reactants, you should be able to balance precisely the amounts you need in order. Basically, we're doing the same thing here. We want to have magnesium and nitrogen as reactants in the beginning, and then we want them completely consumed. So they have to balance each other precisely with nothing left over, no excess.
I have a question. In this exam, could you write the equation or we have to figure out the equation?
If I don't write the equation, that means you have to write it. And you should be, at this point, you should be able to write this equation. Magnesium, you know, it's just Mg. It's not ionic. Nitrogen, you know, it's N. You know, it's nitrogen as it exists around us. So it doesn't exist as N around us. It exists as N2. Pretty much all, the only gases I can think of that are single atoms are the noble gases. Everybody else is a molecule. O2, N2, H2, F2, Cl2, O2. They're all diatomic, at least diatomic gases. All right, next question.
Can we do question 6 from this recitation?
6. Another limiting reactant problem. Okay, this is the last one we're going to do because you should know how to do these by now. All right, so this time you didn't even need to write the equation. Man, I think I'll probably be mean on the test and just say and leave out the reaction, have you fill it in. Anyway, but for now. So first thing to do when you get the question like this, what's the very first thing before, you know, writing down what we know? What's the very first thing to do?
Read the equation of balance.
Yeah, check and see if it's balanced. Make sure. So we got 4 irons, 6 oxygens, 2 times 3, 6. Yeah, we're good. So it's balanced. So we can use it. So what do we know? We have 72.0 grams of iron, and we have 67.0 grams of oxygen. How do we determine which one's the limiting reagent?
The less small. Oh.
The what?
You said what? How can I know?
Which is the limiting reagent?
The one who has a less amount of moles.
Nope. Nope. That is a typical. That is a common error. That's not always the case, because if I need a lot more, like for instance, I need more moles of iron than I need moles of oxygen. So if I have the same number of moles of iron and oxygen, then iron is limiting because I actually need more of it. And so you can't just look at the amount of moles of each one. You need more information. What's the second piece of information? I mean, first, yes, you do need to convert them both to moles. You should at least do that. But you need to do something else as well. So let's get the moles first. So I want moles. So I'm going to put moles on top because that's what I want, and I put moles on the bottom because that's what I want to cancel. So what do I put in for grams for each of these?
$55.845 grams.
5,845, okay. And for oxygen? Oxygen's 15.999, right?
Yeah.
So is that what I put in there?
You have to multiply it by 2.
Yes, there's 2 of them. There's 2 atoms. So we just take our 15.999 and we multiply it by 2. So just 31.998. Okay. So that's going to give me my moles of each one. So how many moles of iron do I have?
Did you multiply your answer by 2?
Multiply what answer by 2?
You said you have to multiply 2 because we have 2 more.
There's 2 moles of oxygen atoms and 1 mole of oxygen molecules.
Yeah, okay.
So I can't use the molar mass of O. I need the molar mass of O2.
Okay.
Yeah, another common mistake. Students make that one a lot.
So we do this for oxygen, for hydrogen, for N2, all of these.
All of them.
Okay.
Yep, all of them. Unless, yeah, if it says elemental, elemental means that's the form that you find the element. So elemental iron is Fe, it's just solid by itself. Elemental oxygen is the oxygen you breathe, that's O2. Yeah, it's the most stable form of the element. That's the meaning of the word elemental. So, yeah, so we have to, so there's 2 atoms. We need to make sure we measure the mass of both of them. So how many moles of iron do I have?
1.2893.
2893. Okay, and oxygen.
2.09388.
Okay. So now I got moles of each one. But I still don't know which one's limiting. What's the definition? There we go. What's the definition of a limiting reactant? Doesn't mean the reactant that there's less of. There's a very specific definition. What does it mean?
It's whichever reagent runs out first, so the reaction can only make that much of the product.
Exactly. It runs out first. Because it runs out first, it limits the amount of product that's made. Once that reactant runs out, reaction's over. No more product. So we need to figure out which one of these 2 makes less product. That's the whole point. And so what you do is you take each one separately and assume that's the limiting reactant. And so basically what you would, the calculation you do is, well, if that's the limiting reactant, how much product do I make? And the second calculation, well, if O2 is the limiting reactant, then how much product would I make? And then whichever number is smaller, that's the limiting reactant. So we need to do both. So we need to do both calculations. So how many moles of Fe2O3 would I make if I was limited by this much iron?
Two.
Nope. No, you need to do a calculation. What do I need to multiply this by to get me here? I need to multiply that by something.
The molar ratio.
There you go. Yes, the molar ratio. So I have iron here. I want to put moles of iron in the bottom because I want to get rid of that. I want to have moles of Fe2O3 on the top because that's what I want to calculate. And so my ratio is 2 to 4. 2 to 4. So basically, for every mole of iron I have, I make half that much product. And that makes sense, right? Because every 4 moles of iron I get 2 moles of product. So I cut it in half. If I had 2 moles, I'd make 1. If I had 6 moles, I'd make 3. Erica, yes.
So we have 2 to 4. Do we just leave it at that, or can we do 1 to 2?
Of course, yeah. Yeah, either way. You're going to have to put it in your calculator anyway. So yeah, you can just divide by 2, or you can multiply by 2 and divide by 4. You're going to get exactly the same answer.
Got it.
Yeah. Yeah, since you're going to be doing it by calculator, yeah, whatever. If you were doing it by hand, then yeah, I would definitely just divide by 2. But I can't divide 1.2893 in my head by 2. It makes my head hurt.
I have a question. So you multiply 2/4, then you multiply mole of
Moles of iron, which is this. That's how many moles of iron I have.
okay.
That's how many are in 72 grams.
Okay, what I will put on the top?
Huh?
In the top, you said mole over 1.289.
I'm sorry.
So we multiply by 1.2893, correct?
Yes.
But what in the top?
What in the top? Oh, moles of iron, moles of product.
Oh, okay.
So I'm multiplying moles of iron, so I cancel moles of iron, and I'm left with moles of product. So after all this, how many moles of product do I get? It's going to be half of 1.2893.
Zero 0.64464.
Yeah, 0.64465. So if all of my iron gets converted to product, I get that many moles. So I'm just going to keep track of these numbers because we're going to have to come back to it. So I have, man, that looks small. So I've got 1.2893 iron and 2.0938802. So I'm going to get rid of that. All right, so that's how much product I would get if all the iron was converted. Now, what if all the oxygen was converted? How much product would I get then? How do I calculate that? So my 67 grams of oxygen are this many moles. How do I convert that to product?
Multiply 2/3 because of the ratio.
2/3 what?
To
Yeah, put the units, always put the units. That helps me. So yeah, 2 Fe2O3 over 3O2. Yes, because then I cancel O2. That guarantees that if I have the units in there, then I know what I've calculated is probably going to be correct. So my O2 cancels, I'm left with Fe2O3. So how many moles is that?
Two 2.79184 moles of Fe2O3.
You sure? You're multiplying, you multiply this number by 2 and then divide it by 3. So it can't be more, it can't be more than 2. It's got to be less.
I got 1.39592.
Yeah, that sounds more like it. So 1.39 something?
592.
592. Okay. So if I convert all the iron to product, I get this much. And if I convert all the oxygen to product, I get this much. So which one's limiting?
Oxygen?
No, if I convert all the oxygen to product, I get more. That's how much product I get if all the oxygen's converted. If all the iron's converted, I get 0.64465. So actually, I'm limited by the iron. Hello? Oh, okay. Yeah, so I'm limited by the iron.
Yeah, correct.
So our limiting reagent is iron. And the mass of iron that's produced, we can just do an easy calculation because we know how many moles are going to be produced. It's this many. So we just convert that to grams. We just multiply with the molar mass of iron 3 oxide and figure out the mass. The tricky thing is, what's the mass of the excess reagent, right? That's the one that everyone has trouble with. So let's do that. So how do we do that? How do we figure out how much excess we have? Oh, damn it. How much excess we have left? I'm going to use this number, 0.64465 moles of Fe2O3, to tell me how much iron I'm going to have left. How do I do that? Damn, got really quiet. So at the beginning, oops.
You subtract.
Subtract what?
You subtract the total mass that was consumed by the mass that was given of the reagent.
So sorry, what do I subtract?
I could be wrong. The mass of the reagent that was used.
Right. The mass of, yeah, we need to know what the excess, so the excess we know is oxygen. Yeah, so we need to subtract the mass of what was used in the reaction, and that tells us what was left. How are we going to figure out the mass of what was used?
You have to convert 0.64465 moles of Fe2O3 to grams.
Nope, don't need to do that. That's not going to help us. Well, actually, I'm sorry. That's another way to do it. There's 2 ways to do it. That's a really good point. There's 2 ways to do this. Actually, that's a great point. Let's do it your way and see if we get the same answer. That's an excellent point, actually. I never even thought of doing it that way. Sorry, I apologize. That is another way to do it. So, how many, yeah, that's a great point. How many grams of product did we make? What mass of iron oxide is produced? We need to, yeah, we didn't answer that question with a number, but actually if we did have that number, we could.
Would we get the moles of 0.64465?
Yeah, so it's just look up the molar mass of Fe2O3. You can just Google it. We'll plug that in. Man, I didn't even think of doing it that way. That's actually much easier. So what's my molar mass of Fe2O3?
So it's 159.69 for the gram.
Okay. So we make a total of 159.69 times 0.64465. So we make a total of 102.94 grams of product. And so remember from all the way back in chapter 1 that when we do a reaction, mass is conserved, right? We have our mass of reactants We have our mass of products, and they have to be the same. So actually, this is a great, yeah, man, thank you for ever pointing that out. It's an easier way to do it. I always did it the hard way. So we know what our mass of products is now. We only make one product, and that's the mass of it. And so the mass of our reactants has to be the same, right? And so since iron was limiting, we've used all 72 grams of that. And so the rest of the mass that's in this product must be oxygen. So the mass of oxygen was 102.94 minus 72.
30.94.
30.94. That's how much oxygen we consumed. And so if we consumed 30.94 and we started with 67, you just subtract 30.94 from 67. So 36.1. So 36.1 grams of oxygen left over. Now, the more complicated way to do it, which takes an additional step, probably just do it this way from now on. The more complicated way to do it is actually determine how many moles of oxygen are consumed in the reaction.
We take 30.94 multiplied by molar mass.
We take what?
You said you want to know how many mole we consume from O2?
Yes. So we do that by taking the moles of Fe2O3 that were produced. And so we put moles O2, moles Fe2O3, and we know that it's 3 to 2. So that tells us how many moles of oxygen were consumed. 0.61465. So that's 0.96698. So that's how many moles were consumed. So we started with this many, and we consumed this many. So the difference is 1.1269 moles left over. That's in excess. And then you just multiply that number by the molar mass. So it takes another step. We do another mole to gram conversion. So we multiply that by the molar mass, 31.998, and we get exactly the same answer. So we multiply that many moles of oxygen by the molar mass, which is 31.998 grams per mole. And we also get 36.1. So that tells me that's the right answer, because we did it two different ways. We get the same answer both ways. Yeah, so you can either figure out from the number of moles of product how many moles of the excess reagent you used, and then subtract that from the total number of moles you had at the beginning, and then figure out grams. Or you can use the simpler method of remembering that the mass of reactions is conserved. So if I had this mass of A and this mass of B, and they made this mass of C, then I can just figure out how much my total mass of reagents is left over. That works even better, or quicker anyway. All right, we've got time for a few more.
Professor, can we do number 8?
Of this one?
Yeah, that's fine.
Oh, sure. Okay. Yeah, so this one is trying to figure out basically how many moles of carbon, hydrogen, and oxygen we have in this particular compound. So we know what we're given is we take 12.1 grams of it and we burn it. So we take 12.1, and I'm just going to call it CHO because it's got CH and O in it. So we're going to burn that. And what reaction is that? When you say it's burned, what does that mean? What?
Combustion.
React with oxygen?
Right, it's a combustion reaction. And so when I do a combustion reaction of something that only has carbon, hydrogen, and oxygen in it, I'm just going to make CO2 and H2O. Those are going to be my two products, right? And so the information I have is that I've got 30.2 grams of CO2, and I've got 14.8 grams of water. So what is the empirical formula? What does that mean? And before we answer the question, we kind of need to know what the hell what are they looking for? What do they mean by empirical formula?
The least condensed formula.
The simplest?
Yeah, that's one way of putting it. Yeah, simplest what though? Simplest formula. What does that mean?
Like CHO, the simplest, like sometimes we have C6H12O6, then we simplify to be 61H2.
But what do those refer to? 6 and 12 and 6. What does that mean in a formula?
The symbol then moleculus equation.
So when I say something is C6H12O6, what am I literally saying? What does that literally mean?
I need 6 mole of carbon with 12 mole of hydrogen and 6 mole
Right, exactly. So it means in 1 mole of that product, I've got 6 moles of one atom, so many moles of another atom, so many moles in another atom. That's the molecular formula. It tells you the precise number of moles of each one. So the empirical formula gives you the simplest ratio of those things. That's sort of what I was looking for. You want the simplest ratio of the number of moles of each one of the atoms. And so we're going to get that from figuring out how many moles of the products from my combustion reaction. So if I figure out the number of moles of CO2 and number of moles of water, what information will that give me? Like why would I bother to do that? What's that going to tell me?
To find how many moles?
Find how many moles of what? I mean, it's moles of CO2. What's that going to tell me? What's that going to tell me about my original product, well, my original reactant?
Because I don't know how much I use it, correct?
Yeah, but why do I bother converting grams of CO2 to moles of CO2? What is that? What information does that provide me? I must do it for a reason. What's the reason for doing that?
Because I need to know how many moles of carbon I use it.
Carbon, right, it gives you the moles of carbon, exactly. The only source of carbon in this reaction is from my original molecule. So this tells me the number of moles of carbon that were here originally, if, with the assumption that all of that got converted to CO2. What about water? What does that give me?
Hydrogen and oxygen.
No, it doesn't give me oxygen, just hydrogen. Now, the reason it doesn't give me oxygen is because there's oxygen present in both the atmosphere that I'm burning it in and in my reactant. And I don't know where that oxygen, I don't know where that oxygen comes from. I can assume that like most of it comes from the atmosphere. And when we do these reactions, we do them in very high pressure to sort of make sure that all that oxygen came from the atmosphere, but I can't guarantee it. So all I can do is figure out the number of moles of carbon, the number of moles of hydrogen. Those are the only two things I can calculate with any certainty. And then we'll figure out what to do with the oxygen at the end. So how many moles of carbon do I have? What am I going to multiply that by?
Molar mass?
Molar mass of what? And where am I going to put it?
Oh.
Grams on top, moles on the bottom? That's the molar mass.
Moles on top, grams on bottom.
Yes, I want to get moles. I don't want to get grams. I got grams. I want to get rid of grams. And because, so CO2 is around 44, I think 44.01 or something like that. We don't need it like super precise. So that gives me moles of not only CO2, but just moles of carbon. And the same thing with water. So if I have 14.8 grams of water, again, I want to multiply that by moles because I want moles. And water is 18.
0, 1, 2, 5, 8.
All right. That'll give me moles of H2. But what I actually want is moles of just H. So what should I do with this number?
Set up a mole-to-mole ratio.
I just multiply this by 2, and that gives me moles of hydrogen atoms, right? Because this is for each mole of water, I have 2 moles of hydrogen atoms. So I figured this gives me moles of water. If I multiply that by 2, that'll give me moles of hydrogen. Does that make sense? Because I don't want moles of H2, I want actual moles of hydrogen. Because I haven't got H2 in my reactant, I've got hydrogen, not H2. Is that clear to everybody?
Yeah.
Can you
Okay. Oh, go ahead. What was that?
Can you repeat it again?
Yeah. So every mole of water gives me 2 moles of hydrogen atoms. And it's hydrogen atoms I'm looking for, not hydrogen molecules. Because there's hydrogen atoms in my
Yes.
in my reactant, not hydrogen molecules.
So we divide by 2?
Multiply by 2. There's two moles of hydrogen atoms in every mole of water. This expression calculates moles of water, the one on the bottom. It gives me moles of water. For every mole of water, I'll get 2 moles of hydrogen atoms. So 30.2 divided by 44.01. So on the top, I've got, man, I need a much bigger screen or something. So I've got 0.686 moles of carbon. And I've got 1.64 moles of hydrogen. Okay? Now, how am I going to figure out moles of oxygen? So I know it's only got 3 things. It's got carbon, hydrogen, and oxygen. So now I know how much carbon's in there. I know how much hydrogen's in there. How am I going to figure out how many moles of oxygen? problem is I don't know how many moles of reactant I have. I just have a mass. I have 12.1 grams of it. I have no idea how many moles there are. So I have 12.1 grams of reactant. I don't know how many moles there are. Could be one, could be the half, could be a tenth. I have no idea. So what am I going to do? I need to take, this is the only information I have. Moles of carbon and moles of hydrogen. I need to use that to get me to grams of oxygen. How am I going to do that? So quiet. Remember, you got two pieces of information you've got grams and you got moles. Right now, I need some gram information. I need some mass information, but all I've got is mole information. So what am I going to do with my mole information to get me to gram information? I guess I just quit.
Multiply it by the amount of the elements that they have based off of the information that was given to us.
I'm sorry. What do I do with the information?
Sorry, not very good with my words. So for
No, I just couldn't hear you. Just my hearing is not great. So yeah, go ahead.
Okay. So for example, for the moles, 0.686 moles, you can multiply it by 12.
Right.
Based off of the how many carbons do we have?
Exactly. The only information I have is grams of the total product and moles of each of the constituent atoms. So I need to move from moles of the atoms to grams, and then I could figure it out. So if I could figure out the number of grams of carbon and grams of hydrogen, well, the only mass that would be left is my mass of oxygen. So that's how I'll figure it out. So if I have this many moles of carbon, I multiply that by the mass of carbon in grams over 1 mole of carbon. And hydrogen, let's just say it's 1, because it's 1.008, but whatever. Grams in 1 mole. Now remember, that's 1 mole of hydrogen atoms. So be clear on that, 1 mole of hydrogen atoms. So don't, since we went to the problem, since we went to the looking at the number of moles of hydrogen atoms, we don't want to multiply by the mass of hydrogen molecules. That would screw everything up. So we want mass of hydrogen atoms. So how much carbon in grams do I have?
Multiply this number of moles by
This.
smaller mass.
Yeah, 0.686 moles of carbon times 12. How many grams of that do I? How many grams of carbon?
8.236 grams.
8.236 grams. And hydrogen?
1.644. Okay.
1.644 grams of hydrogen. And so the remainder has to be oxygen. So it would be 12.1 minus these two. And whatever's left over has to be oxygen. Minus 12.1. So we have 2.2 0.07 grams of oxygen. So if the original 12.1, 8.2 of it was carbon, 1.6 of it was hydrogen, and 2.2 of it was oxygen. So now that we have all that information, to finish, what do we need to calculate to finish this up? So I got three pieces of information. I have moles of carbon, I have moles of hydrogen, but I have grams of oxygen. Oh, sorry, not O2. Oh, I made a mistake there. Oxygen atoms. So the answer I'm looking for is the empirical formula. And we said that that is the lowest ratio of moles of each one of the constituent atoms. So it'd be the ratio of C to H to O. Well, I've got moles of carbon, and I've got moles of hydrogen, but I have grams of oxygen. So what's my next step?
Wait, sorry. Where did you get 2.207 grams?
Oh, because we figured out how many grams of carbon we had from the moles, and we figured out how many grams of hydrogen we had from the moles, and we just subtracted that from 12.1, figuring the remainder that wasn't carbon and it wasn't hydrogen would have to be oxygen. And the remainder was 2.207 grams of oxygen.
Oh, okay.
Yeah. So I'm 2/3 of the way home. What am I going to do with grams of oxygen? So I've got moles of carbon, moles of hydrogen, but I got a mass of oxygen. What am I going to do with the mass of oxygen?
Multiply by molar mass to get rid of gram.
Where am I going to put the mass, molar mass of what?
Oxygen.
Okay, where are we going to put the moles or where am I going to put the grams?
Mole in the top.
Yep. Moles of oxygen in the 15.999 grams. So I have 0.137 moles of oxygen. So, I keep putting O2 there, I apologize, just force of habit. So I've got 0.686 moles of carbon, I have 1.64 moles of hydrogen, and I have 1.38 moles of oxygen. How am I going to turn that into a formula?
Divide by the smallest one?
Yes, because I need whole numbers. I need whole numbers of moles, because there's whole numbers in a formula. So if I divide everything by 0.138, O becomes 1.64 divided by 0.138. H becomes 11.9. And carbon is 4.97. So when I look at that, 4.97 is really close to 5. I mean, within air, I would say that's 5. So C5. And 11.9 is really close to 12. So I'd say 12. And then O1, just leave it. So C5H12O. Now, where you would change this again is if you had something like C 4.5, H 11.9, O. If you had something like that, do not round that to 5. Multiply everything by 2. And so you would get C9, H22, O2. Okay? Or if you had 4.3, if you had 4.33 or something like that, what would you do in that situation?
Multiply by 3.
3, exactly. Multiply that by 3. And so you'd have C13, H36O3. Okay, same thing if you have like 4.67. Multiply that also by 3. Right, so if you get like 0.25, multiply it by 4. If you get 3.3, multiply it by 3. If you get 0.5, multiply it by 2. 0.67, multiply that by 3 as well. Okay? Because remember, you want whole numbers. You want the smallest whole numbers you can. And even if you get some big numbers like this, C9H22O2, there's no number you can divide every one of those by and still get a whole number. So that's fine. All right, I think I have patience for one more before I die. I can barely feel my legs at this point.
Professor, I have a question.
Yeah.
Are you able to upload this video today so we can review it?
Ooh, yeah, I probably could. Yeah, because you'll have all day tomorrow. Yeah, so yeah, I can do that.
Could you please also post the video for recitation 6?
It's only about the 7th time you've reminded me, but yes, I'll try and do that tonight. So is that it? Is that it for questions? You guys want to take a break?
Yes, thank you.
Okay, fair enough. Fair enough. All right, yeah, good luck tomorrow. You'll do fine. And remember, yeah, if you have any questions, I'll probably be like nailed to my desk or actually the dining room table is where I am. So yeah, I'll be here checking in. Yeah, don't ask me how to do a question, but I will. If you don't understand the question, I can help you understand the question.
So it'll be from recitation 1 through 6, right?
Yes. Chapters 1 through 3.
We have to study your slides, correct?
Don't have to. I would recommend it, but you don't have to.
No, because the question, it will not come from these slides.
Well, they're not going to come directly. I mean, they're going to be different questions. They'll be similar, but they're not going to be exactly the same.
Oh my God, yesterday I was studying.
All right, I will see you tonight.
One last question. Is it
Yes.
going to be like PDF form like we had for the lab exam?
Yeah.
Everything same thing, right? We just write on it.
Yeah. Is that a problem for people? Would Word make it easier?
No, that's fine for me.
Because I can post it in Word as well.
No, that's fine for me too.
Okay. Yeah, we just post it in PDF basically because it's a more stable platform. Because if you read a PDF on a Mac or a PC or whatever, it comes out the same. That's the basic reason we use PDF. Because Word documents, who knows what the hell happens to them when they get converted? They sometimes get all screwy.
Yeah, it's due at 10 on Saturday as well, right?
Right.
So all of our exams will be in a form of PDF, all the way to the final.
Yep. Same with the final.
Thank you.
So the final's going to be so long and hard.
Will it?
Yes.
Did you have a date for the final?
Yes, I need to look it up. It's actually it's already decided. basically. All the finals are basically determined, or already predetermined when they're going to be. So I just need to look it up. It's like it's the last, man, it's soon. It's like in 3 weeks or something. Dang.
And it's gonna be also 24 hours?
Yeah. But that'll be cumulative. That'll be on everything, all the way back to the beginning. But it's such a short class, you haven't had time to forget the beginning stuff yet. So, all right, I'll see you tonight at lecture.